talk about the molecular signature of natural selection. And if you look up the website, I already post a review paper on this subject by Nielsen. So I'll recommend everyone read that article. So it's a general description about how the modern molecular evolutionists use the DNA sequence information to detect the signature of selection. And most of the time, we would like to identify the signature of positive selection. But in general, the information can tell us both negative and positive selections. So we'll start with the divergence data. Actually, everybody already know that, but I want to give an overview of the racial test and also talk about the codon-based test. That's mostly by panel. And the first part of the talk is overlap with the previous lecture when we calculate Ka and Ks, but I'll put down like exactly numbers. I know we did a little bit practice, but I want to put down exact numbers how one can calculate the number of silent sites and the average number when we use the sequence information. So let's start with two sequences here. So on the top is the sequence, but we color code the changes between two sequences. And we also put the amino acid sequence corresponding to each codon. And if you think it's not clear, then I want to put down the lines between codons. So now I separate the codon. So it's all in triplets, and every codon has indicate here. Then you can look up the codon table to know which amino acid they encode for. So start with this sequence. Last time we talked about how we are going to calculate the synonymous change and non-synonymous changes. So we'll use the method proposed by Lee, and we use that method to calculate the non-degenerate site, to count the non-degenerate sites, 4-4 degenerate sites, and 2-4 degenerate sites. So that's based on the degeneracy of each codon. So in this table, you can directly calculate the non-degenerate site. That's most of the second codon, like all the second codons are non-degenerate sites. Then you can calculate that. Then you can also look up the 2-4 degenerate and 4-4 degenerate. Now I color code the 2-4 and 4-4 degenerate sites with different color. So that's like a very direct counting on the sequences. So that's what we do for each sequence. So on this slide, there's only one sequence on this slide. So for this sequence, you look at the sequences and you can count the non-degenerate, 4-4 degenerate, and 2-4 degenerate sites. Then based on these three numbers, we can calculate the non-synonymous sites and synonymous sites. As we discussed last time, all the non-degenerate sites are non-synonymous sites. So the black 11 now is down here. Then we'll calculate only a proportion of the 2-4 degenerate sites are non-synonymous. So that's 2/3, right? So 5 times 2/3. That's the number of 2-4 degenerate sites contributing to the non-synonymous. So you can go back to the previous lecture, look at, like we dissect each codon, then look up, for example, if the last nucleotide is a T. So T could change to all the other three possibilities. That's A, C, and G. Among the three possibilities, 2 of them will result to a non-synonymous substitution. And only 1 will give you synonymous substitution. So that's the 2/3 and 1/3 here. So when we calculate the synonymous sites, all the 4-4 degenerate site, the number is 2 on this slide, right? Then you plus the 1/3 of the 2,4 degenerate site. So that's what we discussed last time. The 2,4 degenerate site has two consequences. One is the give to non-synonymous substitution. The other is give to synonymous substitution. And non-synonymous substitution will have 2/3 of the chance, and synonymous substitution is 1/3 of the chance. So that's the two. So you can calculate based on one sequence and calculate the number of synonymous sites and non-synonymous sites by this method. So that's what we discussed last time, but now we just write it in numbers. Then you can count the differences we also discussed last time. So you highlight the differences. Now here we use the double arrow to indicate the differences, and also put the amino acid like with each codon. Then you can count, there's only one non-synonymous change, but 3 synonymous changes. So that's like really just counting. And you can recognize it's synonymous or non-synonymous with the amino acid code there. So then we'll just use M as the differences, number of the differences on the synonymous and non-synonymous, the measure here. Since you have two sequences, then you have to calculate the other one, so the sequence 2. So we calculate the sequence 1. Now we calculate sequence 2 in the same method, like calculate the overall, the total number of synonymous and non-synonymous. And last time I already have someone ask me, this is to remind you what we did last time. If there's a change require 2 differences, then you have to try to analyze the pathway, like possible pathways. And the easier way to do that is just average the 2 passes. So based on this, you can calculate the number of synonymous differences and non-synonymous differences, and also average of synonymous sites and non-synonymous sites. So we put average here because you have 2 sequences. You have to average the 2 to get like the exactly number. So in sequence 1, the number of synonymous sites is 14.33, and that's based on our calculation. Then the other sequence is 13.67. Then you average the 2, you get a number. The average number here is 14. I didn't mention about this part last time. I only used one sequence as example to discuss with you how we calculate synonymous and non-synonymous sites. But since you have 2 sequences, in the real calculation, you have to average the 2 together. So that's the like a slide showing here. So this is what we did with the average number of synonymous and non-synonymous sites. If you did all the calculation, then you can come up with the table here. We calculate the average synonymous and non-synonymous based on last slides. The average of the 2 sequences calculated separately. Then the number is 14 and 4 here. And number of changes are more easier to calculate. So it's 1 and 3. Then you direct divide it. Then so use 1 divided by 14. That's the non-corrected Ka. Then use the 3 divided to 4 is the non-corrected Ks. So that's the total number of sites and total number of changes we use here. And when I say it's non-corrected, because we didn't use the correction formula for multiple hits. Of course, you know the correction model. I have the slides down there, but we discussed last time you can use either 1 parameter method or 2 parameter method to do the correction. But the formula, like the easier like counting method here, we can calculate by hand. It's just by the number of changes divided by number of sites. So that's the number we are going to calculate. And this is the correction. So in our midterm exam, I told you I'll ask you to calculate the real sequences. Then the example will be just like here. So the example I will give you will be 2 DNA sequences and with like a codon there. So I'll tell you how many codon in the sequence. Then I'll provide you the codon table in case you need to look it up. Then I'll ask you to calculate the number of non-synonymous and number of synonymous sites, and also the changes for these two, and give me the ratio. So that will be very easy. So you don't need a calculator with you. So this is like a really just hand like a calculation. You can just calculate easily. And so that's the test we are going to have. So I say for your entire life, you only need to do that once, just like in the midterm test. And I already give you all the details in today's slide. Of course, when we use computer program or any other softwares to help us to calculate either the KAKS or DNDS, it's always correct for multiple hits. So this is remind you, this is simple one parameter method to correct the multiple hits. But in our test, I will just ask you to take the ratio. That will be good enough for our exam.